Hi Geometry. This is Unit 2, Lesson 12 on page 275 of our workbooks. And this is proofs about quadrilaterals. We're specifically going to be looking mostly at parallelograms. So before we get started at looking at some of these conjectures and doing our proof for today, why don't we talk about quadrilaterals for just a second? So can you please turn in your book to, if you go 3 pages, you'll find you have blank pages. This is the page after 277. Let's take some notes about quadrilaterals and parallelograms. So first of all, at the very top, write that quadrilaterals are 4-sided figures. So anything that has 4 sides is a quadrilateral. It doesn't have to have anything special about it at all. So one type of quadrilateral is a parallelogram. So let's separately, do some sort of dividing line, draw a parallelogram, sketch, and label it a parallelogram. So there's some things that you and I know are true about a parallelogram. In Lesson 1, Unit 2, Lesson 1, we learned the definition of a parallelogram is that opposite sides are parallel. So let's mark our parallelogram showing that the top and the bottom, for instance, are parallel and my 2 sides are parallel. So we also have in this unit proved some things about parallelograms. On page 236 of your workbook, you and I proved that opposite sides are congruent. So I know that the top of this and the bottom of this are congruent. I'll mark them with the same number of tick marks. And I know that the side on the left and the side on the right are congruent. They're the same length. I'll mark them both with a single tick mark. We also, on page 254, we proved that opposite angles are congruent. And so, for example, I know those 2 angles across from each other are the same. I'll mark them with a single arc, and I'll mark these 2 with a double arc to show that they're congruent. And I'll make these bullet points because we're going to add 2 more bullet points that are new today to my list as I do these problems. So everything that's true about a parallelogram is also true about a rectangle. So ignore the rhombus for a moment and draw 2 sets of arrows. And one set of arrows is going to point to a rectangle. So all 3 of these bullets are true for my rectangle. And there's something else special about my rectangle. So we define it as has 1 right angle. But really, if it has 1 right angle, it has all 4 angles that are right angles. So let's talk about that for a minute. So first of all, definitely the one opposite it is a right angle. This is now going to bring into another property that you and I haven't looked at so far this year, and that's consecutive angles are supplementary. So let's write down that my consecutive angles are supplementary. And let's remember that being supplementary means that they add up to 180 degrees. And consecutive means 1 right after each other. So for example, the numbers 1, 2, 3, 4, 5, those are consecutive numbers. They are 1 right after the other. So in this picture, this angle, for example, would be consecutive with my right angle. And if they are supposed to be supplementary, if they are supposed to add up to 180 degrees, then this would also have to be a right angle. And then these 2 are consecutive angles. It makes sense they're both right angles because that adds up to 180. And then that's the same reasoning. Either you can think of these 2 as consecutive angles being supplementary or opposite angles being congruent, because everything that's true for a parallelogram is true for a rectangle. And so it has 1 right angle, but really that means then all 4 are right angles. That brings me to another special type of parallelogram, and that's a rhombus. So if you now would draw a rhombus on your paper, and when you draw a rhombus, make it appear that all four sides are congruent. My angles are not 90 degrees, but my four sides are all congruent. So all sides are congruent. So everything that's true about a parallelogram is true for this rhombus. My opposite sides are parallel, my opposite angles are congruent, my consecutive angles are supplementary. Everything is true, but more special than that, all the sides are also congruent to each other. And finally, that brings me to my most special parallelogram, and that's a square. And a square has all the properties of a parallelogram, and it has all the properties of a rectangle, meaning my four congruent angles, and it has all the properties of a rhombus, meaning my four congruent sides. And we're actually going to add some information about the diagonals in just a moment as well. So I want to talk about two quadrilaterals that we use in our workbook that are not parallelograms. So I just want to mention that a trapezoid has opposite sides, one pair of opposite sides parallel. In this particular drawing, what I've sketched looks like an isosceles trapezoid. I'll put that in parentheses because it doesn't have to be isosceles, but it does look like I have sketched an isosceles trapezoid. Isosceles trapezoids are special because they also have a pair of legs. This is referred to as the legs, and the top and the bottom are referred to as the bases. So it has one pair of parallel sides, and if it's isosceles, then it would also have congruent legs and congruent base angles. And so we'll be looking at trapezoids. The other figure that's sometimes discussed, and we've been doing work with kites, the diagonal has been this vertical diagonal right here, but a kite has consecutive sides congruent. So for example, these two sides are consecutive because they touch and they're congruent, and these two sides are also congruent. You can see I whited out the first one I drew. So be careful when you draw your kite. You want to make the consecutive sides look the same, congruent, and the other two sides that touch, you want to make them look congruent as well. So let's go back to our lesson 12, and then we'll look at some information, some conjecture about these quadrilaterals. So going back to page 275, at this point, I'm ready to look at these 5 bulleted statements. So I have number 1, number 2, number 3, number 4, and number 5, and we'll be adding to these statements in the next couple of lessons. So all rectangles are parallelograms. We just looked at that. In the diagram I drew, all rectangles are indeed parallelograms. So are all rhombi, so are all squares. If a parallelogram has at least one right angle, then it's a rectangle. We just looked at that as well. If a quadrilateral has 2 pairs of opposite sides that are congruent, then it's a parallelogram. We're going to prove this in just a moment. It's going to be the proof we're going to do on the next page. So now this is something we're going to add to our notes on quadrilateral page. If the diagonals of a quadrilateral both bisect each other, then the quadrilateral is a parallelogram. And let's look at one more before we flip back to our quadrilateral page. If the diagonals of a quadrilateral both bisect each other and they are perpendicular, then the quadrilateral is a rhombus. So first of all, these two are conjectures, not proven statements. We are going to prove them in the coming days in our class. So let's go write statements 4 and 5 on our quadrilateral notes page. So on this page, I'd like to write underneath a parallelogram that my diagonals bisect each other. So let's use, we'll do light green. So my diagonals bisect each other. So remember what bisect means. It means to split in half. So if I draw in my diagonals for this parallelogram, they are not congruent to each other. I have a shorter one and a longer one, but what they do is they bisect each other. And since I have a 1 and 2 tick marks already used, then I'm going to mark the 2 shorter halves. I don't know if you sometimes see I've got a fly in the room with me, and I think it just did a flyby for you guys. And the longer parallelogram is also split in half. So this is true about my other three special parallelograms, but there's more than that that's true. In a rhombus, we read just a moment ago on page 275 that the diagonals, not only are these diagonals congruent to, the halves are congruent, but that they intersect at right angles. That's true for a rhombus. So my diagonals are perpendicular. I already know that they bisect each other because that's true about all parallelograms. So specifically, if they're a rhombus, they're also perpendicular. If I look at a rectangle and I draw in my diagonals, there's something special about them too. But note what it's not. They do not intersect at 4 right angles. A rectangle is not a rhombus. However, if you look at my diagonals, in a rectangle, the diagonals are congruent. So if it's a rectangle, my diagonals are congruent. And I can prove that using congruent triangles. And I believe we look at that in one of our lessons. So then that brings me to a square. A square has all the properties of a parallelogram. So I know my diagonals bisect each other. It also has all the properties of a rhombus. So I know they're perpendicular. And it also has all the properties of a rectangle. So I know that they are congruent to each other. So now let's go back to page 275. And we're going to pick one of these conjectures. We're going to do the third one for now because I'd like to use a new reason and a proof with you today. So we're going to pick conjecture 3, and we're going to not do a rough draft. We're going to actually do it. We're going to prove that conjecture is true. So our conjecture that we're going to take over to the next page with us is that if a quadrilateral has 2 pairs of opposite sides congruent, then it's a parallelogram. So our given is going to be that we have a quadrilateral with 2 pairs of opposite sides congruent. Our prove statement is going to be that it's a parallelogram. So I've already set that up for you. So if you could, on the next page in the green area, we've got a lot of space. Why don't you guys set up our proof? So I just crossed out the words that were already there on page 276. And I set up my proof. So I'm proving conjecture number 3, and it said if the opposite sides are congruent, then it is a parallelogram. So the sketch that I made to go with this one is over here on the right. Draw it so it looks like a parallelogram. We don't know that yet, but draw it so it appears that way. I labeled it A, B, C, D counterclockwise. And I'd also like us to draw in diagonal AC. And remember what our conjecture started with. Conjecture number 3 started with opposite sides congruent. So let's mark our opposite sides, AD and CB. Let's mark them congruent to each other. Order matters. A goes to C and B goes to D. And let's mark our top and bottom congruent. So AB on the bottom is congruent to CD on the top. So that's my given, what I've just marked in blue. And what I'm trying to prove is that this is a parallelogram. So we're actually going to use something that we haven't used in our proof yet. And I wrote it on this page up above. So I want to pause from doing the proof for just a minute. And I want to look at a statement and its converse. So a statement that you already know is if I have lines that are parallel, alternate interior angles are congruent. That's a reason you've been using in proofs. Alternate interior angles are congruent, and it's always followed when you've been given parallel lines. So today I'm going to use the converse of that. So I'm going to flip it. I'm going to start by saying I have alternate interior angles congruent. If that's true, then I'm going to have parallel lines. I haven't done that before. I haven't used converse of alternate interior angles in a proof. I've only used that alternate interior angles are congruent in a proof. So this will be our new statement for today. But let's go back to our proof. So to prove these conjectures, I use congruent triangles. So the cool things about proving things parallelograms or proving things about rectangles or proving things about rhombi or squares is that I'm going to use these two little triangles. And the first thing I notice that I haven't marked yet is I've been learning that AC, this shared side, would be congruent in both triangles. So I notice when I look at my triangles that I have side, side, side of one of the triangles congruent to side, side, side of the other triangle. So if nothing else, I know that I can get my two triangles congruent. That's not what I'm trying to prove, but that's going to be a really useful part of my proof. So why don't we do that? So let's get my two triangles congruent and see where I can go from there. So for my first statement, it's going to be my given. You could write this on 2 lines if you wanted to. I'm going to write this on 1 line to save space for myself. So I'm going to write everything in the given, and my reason is going to be the given. So then the next thing I'm going to write is my reflexive side that I marked. So I marked this, so I need to put it in my proof. In this case, AC is not congruent to AC. Remember, this is a twist. This is a rotation about a point that's the midpoint of this diagonal. So when it rotates, A goes to C and C goes over to A. So I know that AC is congruent to CA. I've got to flip it. And that's my reflexive property. And once I have that, I have my two triangles congruent by side, side, side. And when I write my triangle congruent statement, I can put the first triangle in any order I want. So I'm just going to say ADC. So I'm going to say triangle ADC. But now that I've done that, I have to match it up with corresponding parts of my other triangle. So if I rotated this triangle down here, my A would come up to C, so they're corresponding, and my C would come down to A, so they're corresponding. So this would be C, B, A when I line up my corresponding parts. So you might say, well, where do we go from here? This is where I want to use my CP/CTC. Once I prove two triangles congruent by 3 specific parts, I now know all 6 parts are congruent. So now I know that my little angle up here is congruent to my little angle down here. They're corresponding parts of congruent triangles. And I know my little angle over here is congruent to the one up above. Again, what they are is corresponding parts of congruent triangles. And so I'm going to label these with some numbers. I'm going to call this 1 and 2. I'm going to call this 3 and 4. This is just going to make writing in my proof easier. I'm not going to have to worry about getting my 3 letters in the right order. Can you do that? Sometimes. It depends on the problem. So now I want to state my angles are congruent. So I want to state that 1 and 4 are congruent by CP/CTC, and 2 and 3 are congruent by CP/CTC. They're corresponding parts. If you're thinking, by the way, hey, aren't they alternate interior angles? You guys, we have no parallel lines yet. That's the point of this proof. So I can't use alternate interior angles or congruent. There's no parallel lines. So you guys, in this statement, this is going to be my statement that's new. I'll do it in a different color. So in this statement, I'm going to say that angle 1 is congruent to angle 4. And I'm going to do it all on one line since it's the same reason. Angle 2 is congruent to angle 3. And that is by CP/CTC. Now, I've done something really important here. This is where I'm going to use converse of alternate interior angles. If I show the angles that are in the alternate interior angles position congruent, then I know I have parallel lines. So, very careful. 1 and 4, if 1 and 4 are congruent, think of your Z that you've got here. That is showing my sides parallel. 1 and 4 would be the alternate interior angles for my two sides. So if 1 and 4 are congruent, that would force my sides AD to be parallel. Sorry, it's just AD with one line above it. Parallel to, now get your corresponding parts. This would be CB. Those are my two sides. My two sides are parallel if 1 and 4 are congruent. Let me get a different color. If 2, this is green, I'm sorry, that was 3 up there, and 2 are congruent, then that's the Z that's making my top and bottom. If those two are congruent, then my top and bottom are parallel. So if these two are congruent, then my top and bottom are parallel. So we can call that DC parallel to now BA, if I'm going to write them that way. So again, I want to point out what I'm working with here. Let me get my two highlighters. So 1 and 4 give me my sides parallel. And then 2 and 3, 2 and 3, 2 and 3, or 3 and 2, I don't know why I keep doing that, give me my top and bottom parallel. So 1 and 4 give me my sides, and 2 and 3 give me my top and bottom. So the reason that was the converse of alternate interior angles congruent. So this is the flip-flop. I knew the angles, then my sides are parallel. So remember, that's the converse. I didn't know parallel sides, and so I said the angles. Instead, I knew the angles, therefore I said the sides are parallel. And now remember the definition of a parallelogram. We define it as having opposite sides parallel. So I now can finish this proof. I can say that ABCD is a parallelogram by definition of a parallelogram, because opposite sides parallel is the definition of a parallelogram from Unit 2, Lesson 1. We said we defined it as having opposite sides parallel, and you just proved that in line 5. So this is a new type of proof from us today. I want to mention just a few other pieces of information. So I'm not sure if I highlighted this in Zoom with you or not. So I want to mention right now that this is just some for more information about quadrilaterals that you should know. One of them is that a parallelogram is a quadrilateral with both pairs of opposite sides parallel. That's the definition of a parallelogram. We learned that in Unit 2, Lesson 1. A rectangle is a quadrilateral with 4 right angles. We just talked about that on our quadrilateral notes page. A rhombus is a quadrilateral with 4 congruent sides. We also talked about that on our notes page. A square is a quadrilateral with 4 right angles and 4 congruent sides. It's a very special, the most special parallelogram. And then a kite, we talked about on our notes page. A kite is a quadrilateral which has 2 sides next to each other. That's my consecutive sides that are congruent. And the other 2 sides are also congruent. And this is not a parallelogram. This is just a quadrilateral. So be careful with those. So all of these statements, though, could be proven by using these congruent triangles. What we've done in our proof so far with parallelograms and quadrilaterals is we decompose it into these triangle shapes that we prove congruent by side, 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 angle, side, angle, side, angle. And we've talked about HL for right triangles as well. So this brings me to your practice. I want to give you a hint for which one. Oh, Number 2 caused a little bit of grief last year. I want to point out something. In some of these, notice that it says, first of all, in A and B, we know that we have a parallelogram. And in C and D, it's talking about a quadrilateral. And because of something, we can prove it's a parallelogram. That's like the second part. So over here, notice that this is talking about a quadrilateral that we show to be a parallelogram. Number 3 talks about a quadrilateral that we show to be a parallelogram. So, for example, these are 2 quadrilaterals we want to show to be a parallelogram. They probably have something to do with 1 and 3, which are statements about a quadrilateral that we talk about being a parallelogram. However, this statement, number 2, talks about a parallelogram already, and number 4 talks about a parallelogram already. So these 2 statements, 2 and 4, probably have something to do with A and B, since A and B are talking about a parallelogram and something that's true. So hopefully that helps this question make more sense to you, being able to break it up that way. That's part of your practice for lesson 12. Thank you very much.